Thank you for watching our presentation. My name is Jose Rodrigo Sanchez Vicarte, and I will be talking about Game of Threads, enabling asynchronous poisoning attacks. This work is done in collaboration with Benjamin Schreiber, Riccardo Paccagnella, and Christopher Fletcher at the University of Illinois in Urbana-Champaign. Machine learning is ubiquitous in our world today. Big data has enabled countless new machine learning applications, and larger models have led to vast ML improvements. However, these factors increasingly pressure compute resources. As a result, machine learning is being pushed more and more into the cloud, leading to the rise of machine learning as a service. However, machine learning is increasingly applied to sensitive tasks, bringing us to a critical question. Is training in the cloud safe? Let's start by looking at the threat landscape for ML in a shared environment. We will use a DNN for image classification as an example throughout the rest of this talk. We start with a dataset and an untrained model. We iterate multiple times over our dataset, constantly updating and improving our model. During this process, an adversary might perform a poisoning or trojaning attack on our dataset, which tampers with the model, steal our model's parameters, steal our training hyperparameters, or even steal our dataset. While this might look pretty bleak, trusted execution environments such as Intel SGX can protect training. Intel SGX provides a mechanism for strong virtual isolation of enclave processes. These processes are scheduled by the OS like any other process, but they are protected from introspection, even against a privileged adversary. So let's add SGX to our training task and see how we do. We can prevent poisoning attacks through input attestation. And since SGX prevents introspection, we are protected from theft of parameters, hyperparameters, and the dataset. SGX can protect training from these attacks. Are we done? Well, spoiler alert, you're watching this talk, so you know the answer will be no. In order to understand how training remains vulnerable, we need to consider the training algorithm itself. Increasingly, data parallelism is leveraged for high-performance training through the use of multiple workers and shared memory. Workers copy the model into a local state, which they use to compute updates. Once computed, an update is accumulated into shared memory with no regard for the progress of other threads. Looking at our example here, worker 1 accumulates an update, copies the model, and misses the update accumulated by worker 2 into shared memory. This way, many threads can collaborate in a racy fashion. Keeping this in mind, let's try to answer our question. High-performance training is racy. Races, therefore, influence the outcome of training. Under the SGX threat model, the adversary is privileged and controls thread scheduling. Today, we present an attack which allows an adversary to influence results by arranging pathological races, which we call APAs. APAs can cause different types of damage. Using APAs, an adversary can cause both indiscriminate damage and focused damage. The goal of indiscriminate damage is solely to reduce the model's accuracy. This is sufficient in many cases. Consider a spam classifier. The adversary wins whether the attack results in an increase in false negatives or false positives. A focused attack, on the other hand, allows an adversary to bias the classifier towards a label of their choice. So in our spam classifier, the adversary can explicitly choose to increase the number of false negatives. We'll start by giving a quick overview on training, specifically SGD and its asynchronous implementation. We'll then present 3 attack variants and discuss possible defenses. Let's start with a high-level overview of a typical training algorithm, SGD. Consider a typical non-convex loss surface, featuring a global minima and a local minima. We're starting from this red X with large gradients, following typical SGD. We periodically decay our gradients by changing the learning rate, allowing us to move closer to a global minimum. Let's see what this looks like algorithmically. We start with our training set and randomly initialize model. We randomly sample a mini batch from our dataset and determine the loss of our model on the mini batch and use backprop to compute gradients and update the model. This performs a single step through the loss surface. We repeat this process until we've iterated over the entire dataset, which is called an epoch of training. Every few epochs, we reduce our step size by decaying the learning rate. At this point, we can exploit data parallelism across batches to get high-performance training. Exploiting this parallelism pushes us from SGD into asynchronous SGD. SGD has a sequential dependence between updates. So if we start at this state x sub 0, we're going to compute an update u of x sub 0 and accumulate it into our model, changing our state from x sub 0 to x sub 1 before we can start computing an update u of x sub 1. Now we continue this sequential dependence until the end of training. ASGD relaxes this requirement for sequential updates, allowing us to have multiple threads computing updates off the same state x sub 0. Now under ASGD, thread 1 can accumulate its update, changing the state, the most current state, from x sub 0 to x sub 1, while thread 0 continues computing an update off an old state. Now, thread 1 can continue computing and applying updates, changing the model frequently many times before thread 0 accumulates its update. This is perfectly normal under ASGD, and training is allowed to continue. The key point is that ASGD has stale updates. Let's consider then how an adversary can leverage this property to perform an indiscriminate attack, the first of our 3 APA variants. We'll start by describing the attack at a high level. On the left, we see a visualization of training which describes how the learning rate changes across epochs. You'll notice that there is no barrier across epochs, meaning the learning rate, alpha, is local to each worker, a common practice. On the right, we see the surface we are optimizing across. At some point, before the first learning rate decay, the adversary halts a worker. We then allow training to continue normally until the last epoch while holding this worker. The model reaches a good state. At this point, we release the worker. Because this worker had a large learning rate, it forced the model to take a large step, leaving us far from the global minimum. In the worst case, we're now in a local minimum. The worker used for the attack can then be terminated by the adversary, and training can be allowed to resume normally. However, it's difficult for the model to return to its previous good state. Another way to visualize this attack is by plotting the learning rate over time. The attack is equivalent to resetting the learning rate to the default value for a single update. It's trivial to consider extending this attack to use multiple threads. The adversary simply allows the worker with a high learning rate to make multiple updates before terminating it. We performed this attack against the ResNet18 classifier for the CFAR10 dataset. This is what we found. Before the attack, the classifier achieved an accuracy of 93%. After a single attack, that dropped to 75%. After a second attack, it drops to 26%. Now let's discuss how this attack can be leveraged to cause focus damage, the second APA variant, where the adversary can bias the network to a label of their choosing. From the last part, we know the adversary can apply a large update. To leverage this update for focus damage, we need to infer the update direction. A key observation from this paper is that we can control update direction if we can perform an update with a biased mini-batch. Recall the training process. Throughout this process, mini batches of data are sampled randomly. Because they are sampled randomly, these mini batches can have a natural bias. Namely, the samples that are pulled from the dataset are pulled with no consideration for their label. Consider these possible mini batches of size 4, where labels are integers from 0 to 3. First, we have an unbiased batch, with an equal number of samples for each label. Second, a batch with 50% bias has 2 out of the 4 samples from the same label. Finally, a batch with 75% bias has 3 out of the 4 samples. The target label of a batch is the label towards which the batch is biased. In this case, that's label 0. There are now 2 important questions we must consider. The first is, how frequently can we expect a specific mini-batch bias to occur? The second is how can the adversary learn mini-batch bias? We discussed the first in the paper and described the second in several slides. For now, assume the attacker can create a mini-batch that has a desired degree of bias towards a desired label. Before looking at results, let's try to form an intuition for why this attack works. Recalling the previous setup, we add a new condition. We wait until a worker with a specific amount of bias is found to halt it. So only when a worker has sampled a mini-batch with a desired amount of bias do we halt it. Then we follow the same process. We hold that worker until the last epoch, and then we release it. Now, unlike the previous attack, batch bias lets us control the direction of the update. While it's not immediately obvious in this cartoon, controlling the direction allows us to move the model to a state where one class is predicted more often than others. Think of it as if each corner had a label, and this lets us choose which corner to go towards. Once again, we perform this attack against the ResNet 18 classifier for CFAR 10. To understand the damage, we consider the prediction rate of the model. This metric says, if the attack batch was biased to label N, how many images from the validation dataset are classified to label N regardless of their true class? Because our validation set has an equal number of images for 10 classes, a model which never mispredicts would have a prediction rate of 10% for each class. We observe, at time 0, that our model is pretty close to this correct prediction rate. After the attack, we see the prediction rate of the target label increase and the prediction rate of others decrease, with a direct correlation between bias in batch and bias in the model. After the attack, the model, as the adversary wanted, is now misclassifying many samples to the adversary's specified target. In the paper, we present an extension which uses more attack threads to achieve more bias. This brings us to a fundamental question. How can the adversary infer bias? Although Intel SGX protects from direct introspection, it's vulnerable to controlled side channels, which can reveal aspects of the execution like mini-batch bias. We use a controlled side channel to infer mini-batch composition. Controlled side channels leak memory access patterns at a page granularity. In ML frameworks today, data layout is public, and image data consumes more than a single page. Building a batch requires accessing each image in memory to copy it into an enclave. To shuffle the dataset, an iterator is shuffled. Shuffling the data in memory is prohibitively expensive, so it's not done. Therefore, controlled side channels reveal mini-batch composition as the batch is sampled. A proof of concept demonstrating this channel under SGX is presented in the paper. Before discussing defenses, we present a third variant which can be used for indiscriminate or focused damage, but with fewer assumptions. Specifically, it relaxes the assumption that we can carry a high learning rate across epochs. Carrying the learning rate across epochs is an implementation decision, which not all asynchronous training frameworks make. Furthermore, distributed systems or parameter server-based implementations might not even have a thread local learning rate. Let's start by visualizing this variant. The key idea here is to manipulate the staleness of many threads. First, we pause all threads immediately after they update shared memory. This gives us a single shared state which no thread has yet sampled. Once all threads are halted, we allow all threads to sample the state and start computing updates. Finally, we accumulate all updates back into shared memory. This guarantees staleness on average. The first update to accumulate has no staleness. The second to accumulate is only stale by one update. The third is stale by two, and so on. The updates are stale overall. Let's see how this affects our model. Considering our loss surface again, and remembering that we now assume all threads have the same learning rate, we start by calculating many updates from the same state. Once finished, we apply them all. Individually, each of these updates was a good, regular update. Together, they acted like a single large update. The key idea is to combine with bias to control direction. Although each update has a different direction, they point in the same direction, the direction the adversary wants, overall. Returning once again to our ResNet18 classifier for CFAR10. This graph presents the loss in accuracy of the model as the number of attack threads increases. If the adversary is able to use more threads, they're able to cause more damage. We overlay the prediction rate of the target label to quantify bias. Predictably, bias follows a similar trend as accuracy degradation. Finally, we consider how to defend from APAs. There are various algorithm-level mitigations which can be done. A private shuffle on the dataset would prevent us from measuring bias. While this mitigates focus damage, it does not protect against indiscriminate damage. Blocking at the end of each epoch prevents the adversary from leveraging a high learning rate. As demonstrated in the final variant, this does not even prevent an adversary from causing focus damage, and it significantly limits performance. We could keep the learning rate in a non-local setting like a parameter server, but this also fails to defend from the final variant. Finally, we could limit thread count, but this only blocks variant 3 at a high performance cost. Although combining some of these mitigations block APAs, doing so still limits performance. The key takeaway is that these are all point defenses, and they all have holes. Besides, we don't know what other attack variants there might be which exploit asynchronicity. To mount a more comprehensive defense, we need to come up with a way to make asynchronous updates inherently safe without hurting performance, and this is future work. Where does this leave us? In answer to our original question, protecting training with Intel SGX is not enough. Training is racy, and the adversary controls thread scheduling, leaving training vulnerable to asynchronous poisoning attacks. A class of attacks which allows the adversary to cause both indiscriminate damage and focus damage. And there are no comprehensive defenses which do not severely compromise performance. Thank you for watching our presentation. We encourage you to read the paper and reach out to us over the next few days on the ASPLOS Slack with any questions or thoughts.